by this in such class. So participants ask me questions about how about the parallel reordering. So as you know, so in this class, so the reordering itself is by single CPU in serial method. But we have some research examples who is doing so parallel graph algorithms for the parallel reordering. So I just so introduced the homepage of such researchers. So he's so Asafu Haidishu Garbamedin. So he's I don't remember that university, but he's in university in USA. So this is a website. Okay, this one. So he's in the Washington State University. So if you so browse his research, you can find some example of the parallel reordering or parallel graph algorithm. So it's also in the under the research. So it's a very interesting and hot area. That's just for your help. Thank you.
All right. Starting from this afternoon, we have Professor Hoshino from University of Tokyo. As mentioned by Professor Nakajima, Professor Hoshino is so young. I think 20-something, right? That's still less than 30 years old. And his expertise is in HPC and especially GPU, and I think and many other things. So it's really our pleasure to have him to teach us about OpenACC. So this is another way to do the GPU programming. So please join me to welcome Professor Hoshino.
Thank you for the introduction. My name is Tetsuya Hoshino, assistant professor of the University of Tokyo. So I introduced about OpenACC and GPU programming. So first I'll explain about GPU architecture and OpenACC. After that, we will start OpenACC hands-on. I'll explain about GPU architecture. So GPU is a graphic processing unit. It is specialized for image processing. So GPU is used in laptop PC or gaming hard or smartphone. So especially using GPUs for general purpose computing called GPGPU or GPU programming. The reason of GPGPU is its performance. So GPU is very powerful processor. Intel Broadwell CPU is installed in Leadbush. So you used this morning. So this is the latest into Xeon CPU. On the other hand, NVIDIA GPU is 9 times faster than Broadwell CPU. So that is the reason of GPGPU. So GPU is used for a lot of area. For example, computational fluid dynamics, bioinformatics, medical images, or data science or AI. So AlphaGo also uses GPUs. So GPU is used for various applications. So because GPU is good at linear algebra. So GPU is very powerful, but GPU programming is not easy. So CPU has several large cores. So large core means that it can do anything. So CPU is good at sequential execution. So on the other hand, GPU has many small cores. So small core means that it has several restrictions. So for example, GPU's core cannot do so branch prediction. So GPU requires so parallel execution. So that is one of the reasons of the difficulty of GPU. So another difficulty is so to treat a large number of cores so efficiently. So today we will use NVIDIA Pascal GPU. So there are two kinds of products of NVIDIA GPU. GeForce is for consumers, gaming PC or someone. And Tesla is for high performance computing. It has double precision cores, a large amount of memory with ECC. So Pascal GPU is fifth generation of NVIDIA GPU. So that is the latest one. So Pascal has HBM2 memory, that is high memory bandwidth memory. And so Pascal is supporting half precision, NVLink, and double precision atomic guard. So this is a diagram of P100 GPU. So this green part is so the CUDA core. So P100 has 3,584 CUDA cores. So this is the reason of GPU is called many core processor. and this is Reedbush H computer node. So each node has two Pascal GPUs. So two GPUs are connected with high bandwidth bus called NVLink, and so host CPU is Broadwell CPU. So that is same as Reedbush U. Okay, let me explain the 5 important characteristics of GPU. First, so GPU's memory. GPU's memory is independent from CPU. So GPU has its own memory, and there are no operating system in GPU. So the user program should start from CPU. So the data transfer between CPU and GPU is required, but the bus between CPU and GPU is relatively slow compared with device memory or CPU memory. The memory bandwidth of P100 GPU is 720 gigabyte per sec, but the bus of read wish is only 18 gigabyte per sec. So users have to minimize this sending input data and returning result. So minimize this data transfer. So second characteristics is hyperthreading. In CPU, the recommended number of threads equals the number of cores. In the case of read wish U, the optimal number of threads is 18. So that equals of CPU cores. On the other hand, the recommended number of threads is GPU's recommended number of threads is 8 times threads or more threads. So GPU requires millions of threads. The reason of this is latency hiding methodology of GPU. So GPU hides memory latency so by using by using context switching. GPU supports context switching by hardware, so it is very lightweight. So if one CUDA core execute one thread, so execute something, start memory load, memory read, and the core waits the finish of memory read. After memory read, start remaining execute. So that is very wasteful. If one CUDA core execute 3 threads, so execute something, start memory read for thread 1, CUDA core switch the second thread and execute and memory read and switch third thread. This switching is very lightweight. So this is GPU memory hiding mechanism. So the hyperthreading is very important for GPU. So third characteristics is hierarchical thread management. P100 has 56 streaming multiprocessor, and one streaming multiprocessor has 64 CUDA cores. So P100 has 3,000 584 CUDA cores in total. So to match this, thread management is also hierarchical, like this figure. So this is thread, and a group of threads is called thread block. So one streaming multiprocessor executes multiple thread blocks, and one CUDA core executes multiple threads. So in addition, threads within the same thread block are synchronizable, but thread blocks are not synchronizable. So to synchronize thread blocks, finalization of GPU kernel is necessary. But this finalization is very large cost. So we have to reduce this kernel code overhead. So fourth characteristics of GPU is warp execution. So warp is a set of 32 contiguous threads within a thread block. So all the threads in a warp executes the same instruction. So the left-hand side case, the instruction is same in warp. It is okay. But right-hand side case, the instruction is valid. It is not available. So if you write a program like right-hand side by using if or else, so it is work, but very inefficient. So the reason for inefficient is warp divergence. So if you like this program, all 32 threads execute if structure and ignore else structure. But the right-hand side case, all 32 threads execute both if and else. In this case, the execution cost is double. So the maximum cost of warp execution is 32 times of this case. So if thread 1, else if thread 2, else if thread 3, else if thread 32 case is so maximum cost of warp execution. And last characteristics is coalesced access. So it is efficient that threads within a warp access contiguous address of device memory, like this figure. It is efficient. In this case, memory access occurs only once. This memory access pattern is called coalesced access. On the other hand, the uncoalesced case, the memory access cost is it is 32 times memory access cost. it is very inefficient. So so these 5 characteristics is most important for of GPU programming. So next, let me explain about the OpenACC. So OpenACC is a set of OpenMP-like directives for accelerators such as NVIDIA GPUs. So AMD GPUs or other main cores are also supported. So the merit of directive-based programming model is so description is simple, so maintenanceability is good, and portability is good. So if you bring a OpenACC program to non-supported environment, compilers ignore the directive safely. So OpenACC is relatively new specification since 2011. So OpenMP started 1997. So OpenACC is really new specification. And the latest version of OpenACC specification is OpenACC 2.5. So there are several OpenACC compilers, PGI, Cray, and Pascal, or GCC. But I recommend PGI compiler because PGI also provides free version, so you can available PGI compiler. So this is the execution image of OpenACC and OpenMP. So OpenMP is fork join model. So the execution image is like this. OpenACC is also fork join model, but OpenACC has a concept of device. So the OpenACC's execution image is like this figure. So suppose architecture of OpenACC and OpenMP is different. Target architecture of OpenMP is so like this figure. OpenMP is so for shared memory architecture. On the other hand, the target architecture of OpenACC is like this figure. So N cores managed with M hierarchy, and it have individual memory. So this is the target of OpenACC architecture. Okay, I explain about the difference of OpenACC and OpenMP. The concept of fork join model is same So same as OpenMP. So the concept of host and device is OpenACC only, and so and that required data transfer between host and device. So the hierarchical parallelism is also OpenACC only. But the latest specification of OpenMP has SIMD, so it is second hierarchy of OpenMP. And this difference is very important. So there are no get thread number operation in OpenACC. So like OpenMP's OMP get thread num. This is not available in OpenACC. So in addition, OpenACC decides several parameters so automatically, such as transferred data size or the number of threads. So, default variable handling is so also different. In OpenMP, all variables are handled as so shared variable. But in OpenACC, Scala variables are handled as first private or private variable. So and arrays are handled as shared variable. So in default, compiler decides the size of transferred data type based on compiler's analysis. But the size of data is sometimes wrong. So you should write your own. So in addition, data transfer occurs every parallel region. So that is very inefficient. So you should write your own. So if you want to use an array as a private variable, you can specify that by using private clause. Okay, next I explain about the difference of so native GPU language. So currently, there are three major porting methodologies for accelerators: CUDA, OpenCL, and OpenACC. CUDA and OpenCL are the most widely used programming model for GPU. Because both programming models achieve very high performance, but productivity and portability are not enough. On the other hand, OpenACC. So OpenACC's performance and productivity and functional portability is good. So we recommend OpenACC. So this is the porting process of OpenACC and CUDA. First, we have to find the bottlenecks and specify code regions to be offloaded. Both CUDA and OpenACC requires this process. In the case of OpenACC, if we insert the kernels or parallel directive, so parallel directive like this. Sorry. So it is a minimum porting process of OpenSCC. In the case of CUDA, we have to parallelize the bottleneck regions and write the kernel codes at this time. So at this time, OpenSCC version is so executable. So in CUDA, we have to manage data transfer between CPU and GPU explicitly, like this green code. In OpenSCC, this process is optional. Now, furthermore, CUDA requires to map the thread explicitly, like this blue. So that is also optional in OpenSCC. So CUDA is very difficult compared with OpenSCC. So I think GPU programming difficulty is like this. So OpenSCC with unified memory is same level as OpenMP parallel. And OpenSCC with data management is more difficult than OpenMP. So I think the kernel tuning of OpenSCC is same level of SIMD parallel of OpenMP. Okay, I'll explain about OpenSCC directives. So there are three major directives in OpenSCC: parallel region directive, data optimization directives, loop optimization directive, and others. So first, I explain about the parallel region directives. Parallel region directive is for sending input data and calculation and returning result. So this directive do all GPU process. So there are two parallel region directive. Parallel directive and kernels directive. Those directives to specify the region to be uploaded to accelerator. Those directives are similar to OpenMP parallel directive. So parallel directive is more similar to OpenMP. So this is parallel region according to my instructions about the kernel parameters. So this is parallel directive. So kernel directive is more automatic directive. So this is device region. I leave the kernel parameters to compiler. That is kernel directive. But the final behavior of both directives is almost the same. So the choice is up to you. But I recommend but I recommend kernel's directive. It is easy to use. So this is the image of the kernels and the parallel directives, directive execution. So parallel directive is manual directive. So it requires the number of threads. So kernels is like this. Please parallelize this loop and adjust the number of threads to device. And parallel is just fork join. Parallelize this loop with n threads. This is the difference of kernels and parallel. So parallel directive has additional clauses to specify the number of threads or data handling. So async and wait clause is for asynchronous execution. Device type clause is to switch parameters for different devices. If and default none is same as OpenMP, and copy clause is same as data directive, say data. And so parallel directive has additional clauses to specify the loop parameters. So this is execution process of kernel directive and parallel directive. At the start of the kernel's region, target arrays are allocated on device memory, and the data is copied to device. And the calculation is execution is so the loop is executed on device, and the result are copied back to host memory, and device areas are deallocated. This is kernel's process. Okay, next, data optimization directives. So data optimization directives are to optimize sending input data and returning result. So it is user's responsibility to maintain the data consistency. So data and enter exit data directives is to specify the lifetime of data required in kernels or parallel region. So this is a combination of allocate and memory copy and memory copy back and deallocate. So data directive is our recommended. So data directive is combination of allocate and memory copy, host to device copy and device to host copy and deallocate. And enter data directive is pair of exit data directive. So enter data directive is the combination of allocate and host to device memory copy. And exit data directive is so copy back and deallocate. So this is a useful case of data optimization directives. If the kernel's region is surrounded by another loop, so in this case, sending input data and calculation and returning result, so everything is repeated. So it is very inefficient. So data directive reduces this sending data and returning result cost. So this is how to use data directive. If insert data directive, so out of the this loop, so the data copy occurred this section, and so if present clause specified, the copy is present clause means so arrays are already present, so the copy is not required. Do not do anything. So in this case, sending input data and returning result occurs only one time. So calculation is only calculation is repeated. So this is enter data and exit data. So if you want to separate data directive, for example, this case, so you can use enter data directive and exit data directive in this case. So this is data and enter exit data clauses. So async and wait is asynchronous data transfer, and main clauses is copy and copy in and copy out, create, present. So copy is combination of allocate and host to device memory copy and device to host memory copy and deallocate. So copy in is allocate and host to device and deallocate. Copy out is allocate and copy back and deallocate. So and present is do nothing. So and And there are present or copying, present or copy out, present or create is also available. So if those so if the array present or present on device do nothing else, do copy, copying or copy out, create. So that is the present or copying. However, in OpenSSE 2.5, copying, copy out, and create same as present or copying, copy out, create. So you don't have to use this present or clauses. So this is so how to specify the range of data. So when the compiler cannot analyze the range, so user should specify the range of the target array. So sub-array transfer is also available by using this. So in Fortran, users should specify the lower bound and upper bound of the target array. So, and on the other hand, in C, the user should specify the start and length of the target array. So, and another data optimization directive is update directive. So update directive is used for present array. So this is only memory copy, host to device or device to host. The last major directive is loop optimization directive. So loop optimization directive is to optimize calculations. Second part. So loop directive specifies the hierarchical parallelism of OpenSSE. So OpenSSE has three hierarchy. Gang is set of workers. Worker is set of vectors, and vector. Vector is thread. So you can specify like this figure. So loop directive is used in parallel or kernels region to specify loop parameter like this. So specify the number of gangs, the number of workers, and vectors. So and loop directive can tell the compiler that this loop is parallelizable or not. So this is hierarchical parallelism of GPU architecture and OpenSSE's hierarchy. So OpenMP thread model is one hierarchy. So threads of multi-core CPU are also managed with one hierarchy. So the OpenMP OpenMP has one hierarchy. In CUDA, CUDA has two hierarchy, thread block and thread, because NVIDIA GPUs are also managed with two hierarchy. OpenSCC has three hierarchy. It is to adjust various accelerators. So this is loop directive clauses. Collapse is same as OpenMP. In this case, three loops are merged to one long loop. So gang worker vector is three hierarchy. So worker loop should be inside of gang loop, and vector loop should be inside of worker and gang loop. So, but it is difficult for beginner to specify optimal parameter. So I recommend not to specify the parameters first. So, and this independent clause is very important. So if there are indirect access, the OpenSCC compiler is very conservative. So if there are indirect access, the compiler cannot judge whether dependencies exist or not. So the compiler doesn't parallelize this loop. So you should check the compiler message and insert independent clause to parallelize. So reduction is same as OpenMP, but there are restriction. Only scalar variable is available. Array is not allowed in reduction clause. So if you implement reduction with CUDA, you have to write those kernels. But same reduction in OpenSCC, just this. So, and the performance of reduction is almost the same as CUDA. So this is one of the reason of we choose OpenSCC. So, and other directives. So one of the important directive is routine directive. So routine directive used for subroutine calling in parallel or kernel's region. And host data directive. So this is used for CUDA kernel code or calling GPU library or MPI communication with GPU direct. So GPU direct is direct communication across GPUs, not via host memory. And this is final directive, atomic directive. So if a variable should be accessed and or updated atomically, so in parallel region, atomic directive is available. So So atomic add is not so slow because it is hardware supported in Pascal GPU. So if you want to use atomic, so surround each atomic statement. So and last, so I explain about so unified memory. Unified memory is so unified memory is to treat CPU and GPU memory as so as if it is so shared memory. So this is hardware supported in Pascal GPU. So OpenACC with so we can available in PGI compiler unified memory. So there is no function about unified memory in OpenACC, but PGI compiler provides unified memory by compiler option. So data optimization directives are ignored. So unified memory is used as so alternative. So merit of the unified memory is this. So user don't need to consider data management. So very easy to use. So easy to use complex data structure like this figure, and there are demerit. So it may not work definitely because it is beta version. So and small transfer becomes slow because transfer will be occurred by a page unit. So that is the end of the OpenACC directive experiment. Okay. I stop the explanation. Do you have questions or?